Question 5. This question is about intermolecular forces. They're the forces of attraction between different molecules. So it might be something like a van der Waals force, a weak force between the electrons in one molecule and the nucleus in the atoms of another molecule. It might be dipole-dipole attractions, where you've got polar bonds within a molecule, and the different delta plus and delta minuses in one molecule attract the delta plus and delta minuses in another molecule. Or it could be something like hydrogen bonding, which is a strong intermolecular bond, where you've got a hydrogen bonded to an oxygen, nitrogen or fluorine, and you've got very different electronegativities between the oxygen, nitrogen and fluorine and the H's. And so you get large delta plus and delta minuses, and therefore the intermolecular bonds, the bonds between the molecules, the attraction is very strong. Give the meaning of the term electronegativity. Well, it's the power of an atom to attract electrons along a bond towards itself. So the power to withdraw or attract a pair of electrons along itself, along the bond, along the covalent bond towards itself. Explain how permanent dipole-dipole forces arise in hydrogen chloride molecules. Well, first of all, you've got a polar bond set up. The reason you've got a polar bond set up with delta plus and delta minuses in the molecule is that the Cl is more electronegative than the H. So the Cl gets a small minus and the H gets a small plus. So it's the difference in electronegativity, with Cl being much more electronegative than the H, that makes this polar bond, with the Cl getting a small delta minus and the H getting a small delta plus. And the dipole-dipole forces, remember that's an intermolecular bond, a bond between one molecule and the next, is where the delta plus on the H of one molecule attracts the delta minus on the Cl of another molecule. So you've got a polar bond within the molecule, delta plus and delta minus, because the Cl withdraws electrons towards itself along the covalent bond and leaves the H plus and the Cl with a small delta minus. But it's the dipole-dipole is the attraction between the molecules, intermolecular bonds. That's what an intermolecular dipole-dipole attraction is. Complete table 4 by naming the shape of each molecule. SiH4, well, Si, silicon's in group 4, so it's got 4 electrons in its outer shell. Those 4 electrons will bond with 4 H's to form 4 bonding pairs. Now, if you have 2 or 3 bonding pairs, then the shape is planar. But as soon as you go above 3 bonding pairs, then you end up with something that isn't planar, with the exception of something like xenon tetrafluoride. But that's a different conversation. But most of the time, if you have more than 3 bonding pairs, you get linear with 2 bonding pairs, you get trigonal planar with 3 bonding pairs, then with 4 bonding pairs it goes into a 3-dimensional structure, which is a tetrahedral shape. pH3, well, what's P? P is phosphorus in group 5, 5 electrons in its outer shell. 3 in bonding pairs with the 3 H's leaves a lone pair, a pair of electrons alone. So you've got a lone pair of electrons and 3 bonding pairs. Again, 1 add 3 is 4, which is more than 3, so it's not going to be planar. So they would normally spread out into a tetrahedral shape. However, you don't see the lone pairs when you describe the shape. So you know there's a lone pair there, but there are 3 bonding pairs. 3 bonding pairs pushed into sort of together into the remaining part of the shape. So you don't see one of the pairs, which is the lone pair, and the other 3 then are in a trigonal pyramid shape. Incidentally, tetrahedral bond angle 109.5. Every time you replace a bonding pair with a lone pair, that 109.5 comes down by 2.5. So it comes down to 107 in the trigonal planar. BeCl2. Straightforward one this. Beryllium is in group 2, so 2 electrons in the outer shell, bonded to 2 Cl's. 2 bonding pairs, therefore it must be planar and it's linear with a bond angle of 180. CH3Cl, carbon's in group 4, it's bonded to 3 hydrogens and a chlorine, so it's got 4 bonding pairs. It's tetrahedral with a bond angle of 109.5. Tick if the molecule has got a permanent dipole. Permanent dipole is when it's not symmetrical. So if you get delta plus and delta minuses, but it's perfectly symmetrical in all directions, then they cancel each other out. So I'm looking for something that's not perfectly symmetrical. Well, tetrahedral is perfectly symmetrical, so it's not that. It's not SiH4. That's perfectly symmetrical and all the bonding pairs are the same. So it's not this one. pH3 isn't symmetrical. You've got a lone pair of electrons and you've got 3 H's along sort of the bottom part of the shape in a trigonal pyramid shape. So that one will be. BCl2 is perfectly linear with a Be in the middle and 2 Cl's at 180. So that one won't have. So pH3 will have. And tetrahedral, even though it's tetrahedral, same as the first one, you've got a polar bond between the C and the Cl. So, and then you've got 3 other H's. So it's not perfectly symmetrical in terms of its polarity. So that one is as well.